Welcome to the screencast for 1.2. So this is all about inductive reasoning. Scientists and mathematicians look for patterns and try to draw conclusions from them. So that's the idea, is we look for a pattern. A conjecture is an unproven statement based on a pattern. So we come up with a hypothesis with an idea based on the previous patterns we saw. So, for instance, in the first example we did, I had a conjecture, right? I had an unproven statement based on a pattern. I had 3 sides, 4 sides, 5 sides, 6 sides. And so I used inductive reasoning, the process of looking for patterns, to make a conjecture that I thought the next side would be 6, that the next shape would be 6 sides. Examples of inductive reasoning. So for instance, the stock market, if you guys ever, right, the traders on Wall Street, the stock market, you look for a pattern with the stocks and you try to make money by guessing which stock is going to keep going up. You can see patterns in numbers such as squares. So in numbers such as squares. So that was another example yesterday. If I have 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. Another example is counting cards. So if you ever saw the movie 21, where they go to Vegas and they start counting cards when they're playing a game at the table. And so being able to see a pattern with the cards, you can, bet more smart. Can make more money that way. And then another is sports. All right, so you can look for a pattern and be able to score more points, etc., etc. All right, complete the conjecture based on the pattern you observe. So our conjecture, remember, it's an unproven statement based on a pattern. So our conjecture is the sum of any 2 odd numbers is blank. Well, let's see. If I add 2 odd numbers, let's try like 3 plus 9, that's 12. If I do 1 plus 1, those are 2 odd numbers, it's 2. So notice anytime we have the sum of 2 odd numbers, we're going to end up with an even number, right? The sum of any 2 odd numbers is even. Next conjecture, the sum of the first n odd positive integers is blank. Okay, so let's see what this is. If I have maybe like 1 is equal to 1. Let's see, if I add 1 plus 3 is equal to 4. So I'm adding the first n positive integers, n positive odd integers. So if I had 1 plus 3 plus 5, 1 plus 3 is 4, plus 5 is 9. I could keep going. 1 plus 3 plus 5 plus 7. All right, 9 plus 7 is 16. Interesting. So wait, if I go through, 1 is 1 squared, 2 is 2 squared, 4 is 2 squared, 9 is 3 squared, 16 is 4 squared. So what we notice is the sum of the first n positive integers is going to be n squared, aka the number of positive integers we have, which is 4. And so if I take 4 squared, that is going to be the sum. So n is just our variable that's keeping track of how many integers are we adding together. The next one, the product of any 2 odd integers is blank. Okay, so remember odd is maybe like 3 and 7. If I multiply that, I get 21. Let's try another one. How about like 3 and 5? That's 15. So it doesn't matter what 2 odd integers we have, the product of any 2 odd integers is going to be odd. Now if you add them, adding will give you an even number, multiplying will give you an odd number. Here's another conjecture. The product of the numbers n minus 1 and n plus 1 is blank. Well, let's see. N minus 1, n plus 1. In order to solve this, we must FOIL it out. So when I FOIL it out, we have first n times n is going to be n squared. O for outer, n times 1 is just n. Inner, for the inner, I have negative n, because negative 1 times n is negative n. And then L for last, negative 1 times positive 1 is going to be negative 1. What you notice is these middle 2 go away, they cancel out. And so the product of the numbers n minus 1 and n plus 1 is going to be n squared minus 1. This is a special case called difference of squares. Doesn't matter what number you plug in for n. I could plug in 3, I could plug in 10, I could plug in 1,000,000. You will always get this as a result because it's what we call a difference of squares, which you'll learn about in Algebra 2. So here is some algebra review. So we are working on plugging in numbers. So computing. So we want to evaluate the expression when n is equal to -4. So every time you see n, you're plugging in -4. So let's try it. So I have 2 times -4 squared. Notice I'm using parentheses. Parentheses are going to be your best friend. It helps you keep track of your signs, the pluses and the minuses. So the first thing we must do is exponents. So -4 times -4 is going to be 16. And then 2 times 16 is 32. And we'll try the next one. N is equal to -4, so I have -5 times -4 squared. You must follow the order of operations. You have to multiply what's inside the parentheses before you can square it. 5 times -5 times -4, well, negative times negative is positive. 5 times 4 is 20. And then we have 20 squared. 20 times 20 is going to be 400. So note, when I plugged it in, you had to do the multiplication inside your parentheses before you can do the exponents. All right, parentheses before exponents. N times n plus 6. So I have -4 times -4 plus 6. We have to figure out the parenthesis, right, what's happening inside before we can actually multiply by -4. So -4 plus 6 is going to be 2, and then -4 times 2 is going to be -8. Try number 4, 90 minus n. So I have 90 minus -4. When you're subtracting a negative, it's the same thing as adding a positive. So 90 plus 4 is going to be 94. So we have 90 plus 4, which is 94. -8n plus 10. So I have -8. And then I'm multiplying by my n, which is -4 plus 10. Now that I've plugged it in, notice I'm plugging it in with parentheses every time. -8 times -4 is positive 32. Negative times negative, they cancel out. And then if I add 10, I'm going to get 42. All right, 11 plus 6 times -4. Just plugging in -4 for n. So note that you have to follow order of operations. Please excuse my dear Aunt Sally. There are no parentheses, no exponents. There's no parentheses to simplify, right? -4 is in parentheses. So I gotta do the multiplication division. 6 times -4 is -24. So if I'm taking 11 plus -24, it's the same thing as taking 11 minus 24. This will give me -13. -7. All right, so sorry, here's 7. So I'm taking, let's see, negative of my n. My n is -4. Then cubing. Notice that the two minus signs are going to cancel each other out because taking this negative here is the same thing as saying -1 times n and then cube. So I'm taking -1 times my -4 first. I have to figure out and simplify the parentheses before I can do my exponents. Now I have my exponent. 4 cubed is going to be 64. And then lastly, n squared minus 100. So this is -4 squared minus 100. So I have -4 times -4 is positive 16. Minus 100 is going to be -84. Perfect. All right, counter example. So an example that shows a conjecture is false. Just because something is true for several examples doesn't prove that it has to be true in general, right? It's just a fluke. You know, the only reason, I get my parking spot in the guest parking every day at school is just because those swimmers didn't show up yet. It doesn't prove that it's my spot. It's just, happenstance. It's just a coincidence. So just because something's true for several doesn't mean it's true in general. So this is called cherry picking. If you take speech and debate, you'll learn about that. To prove a conjecture is true, you have to prove it's true in all cases. So this makes it pretty easy to prove it wrong, right? Because if a conjecture is considered false, if it's not always true. And so a counterexample shows a conjecture, a idea, a hypothesis, conclusion you make. If we can provide a counterexample that shows that our conjecture is false, then that means our conjecture is not always true. All right, example 2. Show the conjecture is false by finding a counterexample. The sum of two numbers is always greater than the larger of the two numbers. So what we want is we want the sum of two numbers that are less than the larger number, right? Because remember, we're trying to find a counterexample that's going to prove this is false. If I pick something like, 2 plus 3, that's equal to 5. Well, 5 is larger than 3 and 5 is larger than 2. So let's rewrite and let's think about what we really need, right? How can I think about this problem to prove numbers that prove this conjecture is false? So for instance, I reworded it, so in order to prove that our conjecture is false, what we're looking for is the sum of two numbers where you add them and it's and the numbers are less than the larger number. So we're wanting the sum to be smaller than the bigger of the two numbers. So for instance, I could have like 2 plus 20, right? 2 plus 20 is not larger than 20. That is not true. Because 20 is not greater than 20 is equal. I could also have like -6 and 4, right? When you add that, is this greater than 4? Is the sum of this greater than 4 because that's a larger number? No, it's not, right? Because -2 is not greater than 4. That is false. So those are some counterexamples. We'd have more examples like, 1 plus 1 is equal to 2, and 2 is larger than 1. So wait, that actually proves the conjecture? We're not trying to prove it, we're trying to find something that proves it's false. So that's not a good one to do. We could do like -7 plus 5 is equal to -2, but -2 is not greater than 5. So this would be a good way to show it. This would be my counterexample. So the hypothesis, right, the conjecture is the sum of the two numbers is always greater. The sum is greater than either the two numbers. Our sum here is -2, but -2 is not greater than my larger number of 5. So that is a counterexample, works. All shapes having 4 sides of the same length are squares. Okay, so you can draw an example that proves this is false. So if I draw something, let's see, all shapes with 4 sides have the same length, of the same length are squares. All shapes with 4 sides have the same length are squares. All shapes having 4 sides of the same length are squares. Oh, okay. So having the same length, so all of these have the same length. That's what these tick marks mean. They all have the same length. But this is definitely not a square. So a rhombus is the name of this. A rhombus has all 4 sides equal length, but no 90-degree angles. Because in order to be a square, you have to have all 4 sides equal and all 4 angles must be 90 degrees. So this is an example. All 4 sides are the same, but it's not a square. All right, any number divisible by 2 is divisible by 4. So what we have to do to a counterexample to prove this is false, think of a number that is divisible by 2 but not divisible by 4. I could do like 22, right? 22 would be a counterexample because 22 is divisible by 4. I'm sorry, divisible by 2. You can divide it by 2, but is not divisible by 4. If you try to divide it by 4, you get 5.5. The difference of two numbers is less than the greater number. Okay, so we gotta prove this is false. The difference of two numbers, so if I take two numbers, let's say like 20 minus 4, so that's 16. And then what it's saying is 16, the difference is less than the greater number. So here the greater number is 20. Okay, well that's true. This is not a counterexample. That's not what we want. We want a case that shows that this is false, that this is not always going to be the case. How about we do like 20 minus negative 2? Okay, this is the same thing as saying 20 plus 2, which is 22. So, is 22 less than the greater number of 20? No, it's not. 22 is not less than 20. Since that's not true, that means that this would be a great counterexample. So 20 minus negative 2 is not less than the larger number, which is 20. So this is a great counterexample. Of course, I'm picking some numbers randomly. You can pick other numbers that also work. Right? You could do 20 minus negative 3, 19 minus negative 4. And lastly, a circle can always be drawn around a four-sided shape, so it touches all four corners of the shape. Let's see. This one's a little harder. So if I draw a four-sided shape, let's see, if I do a square, I could make a circle that touches everywhere. Let me insert a circle. Let's draw a circle. Okay. So I could draw a circle, just need to move it around a little bit. Oops. Move it. Okay. So this is proving it true, right? It's proving it true. That's not what we want. We want a counterexample where that shows that it's not true. So I pick something like this. Oops, I want it to be an actual circle. Yeah, so definitely a trapezoid. This is my counterexample. So a trapezoid reminds me of the desks I had when I was in elementary school. So I can draw a circle. I could draw a trapezoid that's in there. And notice that the circle is not touching all of my points. All right, and then that's it for section 2.